Welcome back, people.
Welcome to another episode of Eigenbros.
Yes.
This week we're talking a bit of quantum stuff, and then a little bit, if we have time, we'll do a grab bag kind of article that I wanted to show Terence, but maybe we'll see.
Sure,
we'll see how
time.
that goes. But yeah, like, comment, subscribe, right?
Yep. Like, comment, subscribe. Guys, make sure you check out Eigenbros.com. Eigenbros on Twitter, Eigenbros on Instagram, Eigenbros on TikTok. And then thank you to our lovely patrons on Patreon. You guys are great. If you guys are interested in our stuff and want to support us, make sure you check out the Patreon for an extra 30-minute podcast every week.
At least 30 minutes.
Yes. And I think that's it.
Yeah, I think that's
so let's jump in.
Yeah, so this whole topic honestly was kind of, how would I say, inspired by an article that came out in Science, or I guess Science magazine.
Yeah,
Google this,
Science Mag, right?
ScienceMag.com. It was came out on September 7th of this year, 2020. The title is "One of Quantum Physics' Greatest Paradoxes May Have Lost Its Leading Explanation," and it has to do with like collapse theories and stuff. And in particular, this one postulate where gravity causes collapse was one of these like competing, I guess, collapse theories of trying to explain, I guess, the problem of measurement in quantum mechanics.
Yeah.
And the gravity hypothesis traces its origins to Hungarian physicist. I don't know, Terence, you might do a better job at pronouncing.
I don't know Hungarian. Oh, fuck. There's no way. It looks like Carolee Hazy. Phrygius.
I'm not sure what that is. Sorry.
Yeah, I don't know Hungarian, bro.
Yeah. I'm just going to try my best. Carolee Hazy Phrygius. In the 1960s and Lajos.
Sorry to the Hungarian people in the audience.
In the 1980s. The basic
butchering your language.
Yeah, the basic idea is that gravitational field of any object stands outside quantum theory and it resists being placed into awkward combinations or quote-unquote superpositions of different states. So if a particle is made to be...
Slow down that reading, Juan.
Okay.
Can't even understand you.
Sorry. So if a particle is made to be both here and there, its gravitational field tries... Basically, the gravitational force tries potential... would cause the collapse of the state. Because the gravitational field or potential cannot endure the tension of the particles like just existing in free space for so long, and it collapses and forces the particle to...
Cannot endure the tension. What does that mean?
I think the people are trying to combine a GR picture into the quantum
mechanics.
Yeah.
They do that in quantum field theory.
They try to do that in quantum field theory, yeah.
So what did quantum field theory say?
I don't know. Didn't take that semester.
You took many body though.
I did, but it doesn't talk
no insights.
About that's quantum field theory applied to particles and solids and stuff.
So you didn't learn anything.
Well, I didn't learn anything about the cosmos, bro.
You can't extrapolate it, one. Come on, man.
I can try, but I mean, like, yeah, it's just like how do you have particles that I would say like come up from the void, I guess. How would they interact with the gravitational field? And if they come up from the Fermi sea, I guess, how would you deal with that? And how does the potential handle that? No. I'm guessing
that's a hard ass question.
I'm guessing that's maybe something that they asked themselves. But anyway.
Okay.
Yeah. So Penrose actually was a proponent of this collapse postulate that gravity causes collapse.
This is the GRW theory. What was it?
No, I think this is something else.
Okay.
Yeah, GRW is another theory that I guess I will definitely get to, but
okay.
Well, because Penrose had the thought that I think he agrees. A lot of physicists agree that the anthropocentric notion that humans cause collapse, which we don't like.
Well, I don't know if they're saying that humans cause collapse necessarily. I'm thinking they're just saying any kind of macro scale object causes collapse.
Well, that's the interpretation we take now. But back then, it was like the fact that humans are observing a quantum state. You can change. That was a lot of the woohoo kind of like stuff.
Okay, maybe.
Going
I think
around.
that's also a misconception. I don't think scientists really consider that as the interpretation. I think they
I think so, because this was debated.
No, I think they just were using that as a kind of like allegory or kind of a fluffy or mystical sounding way to really drive the point home. But I think they were all real clear about knowing that it's not conscious. Like, it's not like some what the bleep crap. You ever seen that movie?
Yeah, what the bleep.
Yeah, what the bleep is one of these stupid science films. I say science in very heavy air quotes because it's basically like a cultist hippie movie.
Yeah.
And they kind of ascribe these things like, consciousness. Particles can consciously understand when they're being sensed or something, and then that's why they collapse. But
yeah.
I think that's because of the rhetoric that they used back in the days, like Einstein and Schrodinger and those guys, that gave that kind of false
the observer
image.
They were using language in relativity, observers.
Yeah, exactly. But I think they well understood that it wasn't an actual physical observer because they were measuring the particles, right? And you can't even see the particles anyway with your naked eye, so they knew it was from a measurement from a machine, right? There's some kind of machine that's taking that actual measurement, that's counting those particles or sensing them somehow. It's not an actual physical human eye.
Sure.
So I think they're well aware of the separation between humans being the observer and then some macro scale object being the observer.
Yeah. Well, that's kind of like the whole thing is like a lot of them still had the problem of like, the philosophical problem of like, what happes to the state? Does the state exist because we're not observing it, kind of thing? Does a tree, when a tree falls in the woods, does it make a sound?
Yeah.
That's kind of the question.
Right.
Of like, does it exist?
Right.
Yeah.
Yeah, it's an interesting question.
Do the states exist? That kind of thing. Anyway. I think for the longest time, there's some proponents of quantum mechanics that had this kind of idea, or I guess accepted the notion that humans do, when they interact with a quantum mechanical system, that they change the outcome. Now, I think this was highlighted in one of our episodes, I think in the history of quantum mechanics, right?
Maybe so. I can't remember. It's old.
We might be retreading some common ground, but there was a quote that I think I highlighted that it was like, I think it was Einstein discussing with what's his name? Wigner? No, not Wigner. What was his name? There was another famous quantum mechanics guy. He was just like, so you're telling me if I turn around and the moon doesn't exist unless I look at it? Is that what you're telling me?
Yeah.
And he was just like trolling Einstein because Einstein was like...
Well, I think Einstein was asking.
Oh, it was the other way around. Yeah.
Because Einstein's like, he doesn't believe any of that stuff.
He does. Yeah, he didn't. Yeah. So, and he was just like, the other...
That's what the math says.
It's just like, something you're telling me. He's like, you're telling me something doesn't exist unless I interact with it, unless I observe it, which is a measurement. This highlights the measurement problem, I guess, in quantum mechanics in general, right? Like how a macro state object interacts with a micro state object,
right?
A quantum mechanical system,
right?
Yeah. That's like the analogy I give is like you're like a bowling ball, and the quantum mechanical like system is like a pin needle, and you are coming to interact with it. You want to measure its position or velocity or something, and then you just... How are you not going to fuck it up? How are you not going to mess up the...
Right, but that also might be a misconception a little bit too.
Okay.
Which I think it might be. I'm not completely convinced yet because quantum is one of these things where, you have to build your quantum intuition. Yeah. And like, I've been away from quantum for so long, like I feel like as I've been away from it, my intuition kind of dies a little bit. Okay. So I forget if this is true or not, but what you're saying is kind of this, an example I've heard like Neil deGrasse Tyson give that I think might be kind of a misconception where he's saying that like the only reason we can't measure a particle's position in space is because it's like, if you're throwing, like you said, like a bowling ball at a small object, then that small object, as soon as you hit it, it bounces away. But I think that's actually kind of a misconception. I think it's more than just that. I think it's actually, even if the object is not a bowling ball, like if you say two particles,
you can probe it with you can send a particle with a certain energy into. You can have two particles interact.
Yeah.
In the same energy scales. Yeah.
Like let's say like this. Let's say if it was like an electron interacting with a tauon,
Sure.
Like a tau particle is hugely massive, right?
Yeah.
An electron is very tiny. If the electron is your interacting particle, you're still going to get a collapse from that tau particle.
Yeah.
So it doesn't matter if it's like a really big. It doesn't matter. It doesn't have anything to do with like the resolution of the measuring object that you're using.
Yeah. No, but I'm saying humans interacting with the system, it's not like you do change the outcome of the system, but it's not like you as a conscious, like you can will things into existence. This is the kind of notion that you kind of get that's a little wooey, like you can't just you can't just
You're talking about the moon analogy.
Yeah.
Okay,
but this is the extension, the absurdity of the situation where even Schrodinger highlights, I guess, in this cat in a box scenario, right?
Yeah.
It's like you can't will matter or whatever into existence and not know.
Yeah, I think the way you're saying it is a little bit off, but I see what you're saying. It's like the Schrodinger cat analogy is basically saying that it's trying to highlight the absurdity of saying like either if the cat's dead or alive in a box, because he's basically dependent on whether that radioactive particle in the box decays and it unleashes like some cyanide or some poison to kill the cat. And he's saying that shouldn't be the case. There needs to be some way to be able to tell what's happening inside of this system, I guess.
Well, because
at least
the argument is that now because the radioactive atom in the box is now coupling the cat in this superposition of states, and now you measuring
it's now coupling the cat. Yeah.
So now you coming in, see for you have no information about the state. You're gonna peer into the system.
Yeah.
And
well, you collapse it as soon as you peer into it.
Yeah.
But it's just showing us like now the cat is completely entangled, and cat's a macroscopic object, so it's like, does that make any sense?
Are we all entangled?
Right.
that was the Eugene Wigner proposition where he's like if I tell a grad student to do this quantum measurement, and then I call one of the postdocs in the lab at a certain time to report to me the result. Is a postdoc and the grad student in this superposition as well?
That's a very interesting question. This is where quantum gets really weird and freaky.
This is why like the collapse module is kind of like a huge philosophical problem, I would say.
Yeah, so wave function collapse is quite unusual. It's really hard to even try to wrap your mind around, even to this day. I mean, I guess this is, we shouldn't feel bad because, like everybody says, the famous Feynman adage is, if you think you understand quantum, then you really don't understand. But maybe one day.
I think we're just comfortable with it.
Yeah. And we're more comfortable because of the math, really, right?
Yeah.
I don't think anybody can really understand from even like a podcast. You can't really understand quantum mechanics just from listening to it, because it's just filled with, even if you can understand and latch onto the words and kind of get a feel for what they mean, it's not really convincing until you see the math. The math is really the only thing that convinces me of it.
True.
Because otherwise you're just like all this stuff, you can say it, but like, where's the proof?
Yeah.
And the only real proof is you either have A, experimental proof, or you have B, mathematical proof. And then the experimental proof, you're just going to be like, what is going on here?
Yeah.
So really, the math proof is really the only thing that kind of justifies everything, right?
Yeah. But in this study that's in the Science journal paper, Diossi and other scientists looked for one of the many ways, whether by gravity or some other mechanism, that a quantum collapse would reveal itself. They argue that a particle that collapses would move randomly, heat up the system, which is a part of, and if a particle is charged, it will emit a photon of radiation as it moves around. And multiple particles will be subject to the same gravitational potential, and the idea is that they'll all amplify, and you will emit a photon in unison. But to test this idea, they built a detector, and it looked for like basically an excess of X-ray and gamma rays from this nuclei that they prepared. And so what they found was that, Penrose's model, because remember he was a proponent of this gravitation collapse thing, predicted 70,000 such photons. He said you should see some collapse effect in this particular experiment. He's like, but we don't. So it suggests that gravity is not, in fact, shaking particles out of their quantum superpositions. So we've ruled out, at least through one experiment, 30 years later, that gravity does not seem to cause collapse.
Oh, I thought it would have, which is interesting how it doesn't.
Well, like the thing is, I was thinking when I heard about this, I was like, well, that would seem like it would be like a second order correction kind of thing, right? Like I was saying, like it would. Do you know what I mean? Like
I think, but expand on that.
It would be like so in physics, like sometimes we talk about potentials, but potential energies, but you add, there's like secondary term effects that are so small that they're negligible almost. Yeah,
if you look at a math equation, right, you can see it a lot of times in like Taylor expansions. So if you're familiar with what a Taylor expansion is, this will make sense to you. But you get like a Taylor expansion usually has some kind of polynomial equation. So it'd be like x plus x squared plus x cubed or something along those lines. And when Juan is talking about second order corrections, it's like the x cubed, the x to the fourth, and all these things where it starts to become negligible as you look on down like an infinite series that somehow quantifies what you're looking at here. And in physics, you usually take up to like the second order, which would be like the x squared or something like that. Yeah.
Like the linear term is usually the one that captures most of the phenomena, I guess. And it's more it makes a lot more sense when you look at a graph. Like you see how when they add polynomials, like or more terms, it becomes more accurately fitting to the picture of the realistic function that you have.
Right.
And I think it's the same way like that in quantum mechanics. Say if you're building a Hamiltonian, basically like the total energy of the system. Adding second order corrections might give you more accuracy in the digits of like your energies, but it's not going to change the physical picture much. You know what I mean?
I see.
Yeah. That was my intuition with the whole gravity causes collapse thing.
Okay.
But intuition is often wrong, which is why you need experiments like this, which is why you need guys like the team that just confirmed this, like. Because gravity causing collapse, that's a legitimate question.
Yeah, actually, I would have actually thought maybe it does.
Yeah, me too.
Because you think of anything that interacts with a quantum system as collapsing it, but that's really interesting.
Yeah, because particles have mass.
Yeah, but I guess it's all the EM wave from the particle, right?
Maybe
the electromagnetic force that it feels from the charge.
Yeah.
Who would have thought? I guess another good way to test it would be somehow with like interacting with like a neutron or something, right?
A neutron.
Yeah, because a neutron is a neutral particle, so it has no EM radiation. So if you have a neutron that interacts with a charged particle or something, or somehow like a neutron,
a neutron, proton or something. That's how they tested it.
Yeah. Does neutron has spin though?
Yeah, it does.
So you can even have two neutrons interacting, and you should just see if the spin will collapse or not.
Well, here we go. Terence just came up with a new.
I don't know if that's stupid or not, though.
Well, they were only I think their model predicted that they'd had to use a proton to get a photon emitted from this process. So I think they were looking for a process to measure if gravity causes collapse, that they would see 70. I guess like Penrose is saying, his model showed 70,000 photons emitted, but I guess it was nowhere near that amount. Either his model is off or gravity does not cause collapse, definitely. Now, there were experiments I remember being done in ISS, or physicists wanted to do quantum mechanic experiments at the ISS.
Okay.
Because they wanted to see if the Earth's gravitational field was
strong enough to affect it?
Yeah.
Interesting.
Yeah.
And I guess it was inconclusive?
I mean, I don't know if they actually went through with them.
Oh, I see.
But I mean, this one was done on Earth. But this is why other physicists, I think, maybe are definitively saying, like, we can't rule it out. We can't rule the possibility out because we're still doing these experiments in a gravitational field.
Right.
So
Interesting. Very interesting.
yeah.
Yeah, there's a lot of enlightening things we can learn still with quantum. I mean, it's probably the forefront of physics right now, right? I mean, of course we have like quantum field theory and whatnot, but I guess it's still quantum at some level, right?
Yeah.
Just has a, I guess it's the
Fancier math.
Yeah, the fancier version with extra stuff. You know,
It's
got a
quantum
little
mechanics with gravity in it. Right?
Yeah. I think because it has gravity, right?
Yeah.
Okay.
Um,
It's still incomplete though. It's close. Feels
Yeah, yeah.
close.
we're close. But should we tell the group or the people here what the hell we're talking about if they don't know, like
What's that?
what quantum mechanics, like the collapse stuff, like
Oh, you want to go into the collapse article?
yeah,
Sure,
because
let's do it.
there's a formalism, right?
Wait, who's the article by?
Oh, this article is, by the way, this is a great resource. If you want to understand everything about collapse, well, not everything, but understand the collapse theories in a more philosophical framework, a more metaphysical framework, just go to plato.stanford.edu. That's Stanford, the STANFORD, Encyclopedia of Philosophy. They have a whole, basically sort of what could be a thesis about what collapse theories are.
It might be actually, right?
It might be somebody's work. I mean, look, it was a substantive revision May 15th, 2020. So somebody just
Okay.
revised this. And the last time I looked at this was like several years ago.
Yeah. It's a good article.
It's a great article.
Or whatever you call it.
Yeah, it's a great
Paper thing.
Yeah, paper thing.
Yeah,
I would love to find who wrote this and then talk to them because
It's got no author on it?
I don't know. I mean, the man or the woman who did this, like, they look at this. Look at all the supporting bibliography. They have a ton of. It's. Let me just say that it's well. Oh, here we go. It's Giancarlo Giardi and Angela Bassi at Stanford, I guess.
Okay.
So shout out to them.
Giancarlo and Angela.
You know what?
Good-
What might be a
good
good
stuff.
idea if we talk to them?
Talk to them.
Have them talk about.
On the podcast?
Yeah.
Oh, there's
That'd
an
be
idea,
great.
Juan. We
That is
probably
great.
could get them
We probably
too.
could get them to talk about collapse theories. So that might
Unless they're famous. Then we
that might
probably
happen, folks. That might happen.
won't. It's a good idea.
Yeah, but I guess just to preface it, like with the formalism of quantum mechanics, right? You
Mm-hmm.
have, I don't know if you kind of want to highlight this,
Oof.
just because Terrence is.
Damn it.
I don't want him to get sleepy over here. I don't want to get sleepy, Terrence.
Let's see. I get sleepy when I read, though.
No, I guess just highlight some of the stuff that you think would be
All right,
would be necessary.
It says, so I guess I'll just read it. So it says, the formalism, a concise sketch, the first paragraph. It says, let us recall the axiomatic structure of quantum theory.
Yes.
So states of physical systems are associated with normalized vectors in a Hilbert space, a complex, infinite dimensional, complete, and
Yes.
separable linear vector space equipped with a scalar product.
Mm-hmm.
So if we break that down, for people who may not be familiar, just breaking it down again, so it says a physical system is associated with normalized vectors. So normalized vectors are just saying that they're vectors with a length of 1. So it's building for you basically I don't want to say a 3D space. It's actually an infinite dimensional space, which you can't really imagine, right? But mathematically, this is a useful tool.
And it's infinite. Well, just for the record, it's infinitely. We say infinite dimensions because you get to choose the amount of information that you're going to measure. Or in your system.
Yeah, and it's not really even describing anything physical, right?
Not yet.
It's like a mathematical tool.
Yeah.
So you're using dimensions as a mathematical tool, and basically says it's a complex, meaning that it can also take imaginary values. So that's the square root of -1.
Mm-hmm.
Complete and separable linear vector space. So that means the equation can be
Separable.
Yeah, I guess that
Right, that's
doesn't really
probably the best
describe
way to
much
put
though. Equipped with a scalar product. So the scalar product, you can do certain kinds of multiplication, which would be dot product multiplication.
Yeah, scalars are more like magnitude, like you have a number object.
Oh yeah, sorry, I messed it up.
As
I'm
opposed
thinking
to vectors, right? Like vectors, you can do transformations. Like scalars, you can do transformations on them and they'll look the same.
Yeah, so it's like you can stretch the vectors that are describing your system in that infinite dimensional Hilbert space.
Yeah.
So since linearity implies that the superposition principle holds, if F is a state and G is a state, then for A and B arbitrary complex numbers also blah de blah. So they give some equations saying some state K is equal to A times a state F plus B times a state G.
Yeah, and we'll put this on the YouTube.
Yeah, so basically this is just describing kind of like the mathematical framework for setting up a quantum state. So you can always pretty much see a quantum state in that form. This is using the Dirac notation where it's just saying that you have some kind of state that has some eigenvalue multiplied by some eigenvector, and that's it.
So what are have we ever explained what eigenvalues and eigenvectors
I don't know if we have.
I don't think we ever. That's our namesake, man. We have never explained it.
So basically, an eigenvalue is a number that is associated with
the vector.
With the vector that doesn't change as you morph the space it's in.
Yeah.
So what does that mean? So it means like if you have a vector, let's imagine there are certain vectors that when you make transformations in the state. So let's imagine if you have like a transformation of your space, you can stretch your space. So if we imagine literally in real life, let's say if you stretched the space around me and Juan, you know, we would be all stretched out and whatnot and look weird. But if you stretch space along certain dimensions, there are parts that may not look any different. Mm-hmm. So how can we make an example of that?
When you say they don't look so different, what do you mean by that?
Yeah, so like if you had some kind of so let's say if we have these books, right?
Sure.
So if we stretched our physical space with these books along the axis of the books, there would be an eigenvector along the horizontal direction here. Mm-hmm. So it would just be the letters and stuff would get stretched out, but you can just multiply them by some number and you'll be able to get the same value back. Yeah. So since you're stretching the space along a direction where the book will remain unchanged, that's what you would call an eigenvector and the eigenvector would be the actual vectors that compose this book's physical structure, and then the eigenvalue would be how much you stretch it by. Yeah. Yeah. Does that make any sense?
Yeah, it does. It does. It's sort of like like you could think about like the minimal ratio, like it's sort of like aspect ratio. Have you ever heard about that? Aspect ratio?
Yeah, sure, with computers and stuff.
Yeah, like or for images and stuff. Like you preserve. It's the smallest unit that you preserve the information of the book, right? Like, like you basically have the original aspect ratio of the book, but
you can multiply by some number, and you can increase let's say the resolution, but then the aspect ratio can still be the same. It's like when you have different like 16:9 aspect ratios, or it's like the 1280 by 720. But then there's also the 1920 by 1080 or something. They're the same aspect ratio. It's just one is bigger than the other. So you're literally just multiplying that by a value, scaling it. Yeah. And that would be like what an eigenvalue does to an eigenvector, let's say, in some sense.
That's probably the better analogy that we could probably use. But yeah. And also they call it eigen because it's like a common I think it's a German word for common, right?
Yeah, something like that.
It's like common
or same or something,
or same vectors, same values. I don't know, something like that.
Yeah, some fancy German.
Yeah.
Okay, moving on. So it says for number 2, I'm going to skip some of that stuff. Blah de blah. So number 2 says observable quantities are represented by self-adjoint operators B on the Hilbert space containing the possible states of the system. So I forget what the hell self-adjoint means.
Self-adjoint, I think it means like the how would you
call that U thing, the union,
the unitary thing. How an observable, basically a measure. What is it called? An operator multiplied by the dagger, basically the
Hermitian.
I mean, you say ultimately that it's Hermitian, but like it's
the
operator.
The conjugate transpose. What you're saying?
Thank you.
Okay.
I cannot think of the freaking word.
It's a lot of jargon.
It is. There's so much jargon that means the same that almost there's very small minutia. So you're going to get a lot of words thrown at you in quantum mechanics, like self-adjoint,
and I don't know
conjugate transpose.
Yeah.
What does it mean?
Is that what it means?
Yeah, I think it's conjugate transpose.
Oh, okay.
I believe it is.
Let's hope
I'm
you're
gonna
right,
correct
Juan.
it. No, I'll correct it right now.
Okay.
Because it's one of these words that there's a lot of shared language in linear algebra and in quantum mechanics.
Okay.
Right?
Yeah. And the thing is, with linear algebra, it's like you can be learning the same math, but you're just learning different words for a bunch of stuff.
Yeah. I mean, the conjugate
like
transpose.
It does the same thing as,
Yeah. It's called, it's basically, it's a Hermitian conjugate, or the adjoint matrix.
Okay, so it is a conjugate transpose, right?
Yeah, I believe so.
Because Hermitian matrix is, you're basically taking that matrix and multiplying it by the conjugate transpose to give you back the identity.
Yeah, exactly.
Okay. So it means, so it just means that basically this is mathy shit, basically.
But
so it's just saying that.
I think we had this discussion. Physically, it means that like the object is reversible. You get the same thing back. That's what a unitary operation would be, right?
Yeah, but what does that mean in real life?
In real life,
you're still saying mathematically.
I mean, like that's a mathematical. We're describing something like you perform an operation.
Still getting mathy.
No. You perform an operation like, let's say you're measuring the momentum of a particle, and that's your momentum operator acting on the eigen. How would you say the eigenstates of the Hamiltonian?
Okay, sure.
And then you do the reverse, which is the conjugate transpose of that.
Okay.
Or you sort of.
What's the reverse mean though?
In physical real life?
Yeah. Because I don't even know what that means.
Run the clock back, bro. I don't know. Yeah, how do you
this is a hole in my knowledge.
How do you do a physical measurement of momentum in reverse? I guess you could because it's a vector, so you would just I guess
you're transposing the vector.
Yeah.
Okay, so this is some mathy shit.
That's what I'm saying.
It doesn't really translate to real life.
Well, it should, because we're describing something in real life in some sense.
Yeah, but quantum mechanics almost is like, do imaginary numbers like?
Yeah,
can you really describe that in real life?
I see
right?
what you're saying.
We're working in infinite dimensional Hilbert spaces,
That's
right?
true.
We're already failing to describe a real picture.
That is very true. Yeah,
So
I think you're right.
So it may not even
hard.
be something you can analogize
really
to real life.
Yeah, I think Terence is right. Something you can't really imagine.
Yeah, so just know that that's what the hell's going on. Some crazy shit behind the...
I like to think about it as such. Like you reverse... You're basically doing a reversal.
I don't like what you're saying with reverse, because it almost like it makes it sound like you're actually implying some realistic image somehow, which is not true. It's like you can say maybe... I would just say conjugate transpose.
Okay, all right. Fair enough.
Because like what is reverse
It's
mean?
really... Okay, yeah. If you want to be real technical, yeah.
Yeah. So it says basically, again, observable quantities are represented by the self-adjoint operators B on the Hilbert space, which is that infinite dimensional space we were talking about, containing the possible states of the system. So that means that all these possible states, so let's say if you have a particle in real life, right? Like your particle can be either up or in a spin up or down state, or it can be in a superposition state of up and down. Those are all actual physical states that a system can be in. Now, it says the associated eigenvalue equations, so B acting on a state BK equals BK acting on state BK. So this is basically just saying that some mathematical thing where it's saying that the operator acting on the state is equal to an eigenvalue acting on a state, which is kind of related to the analogy me and Juan were talking about with stretching the book. Yeah. And the corresponding eigenmanifolds, the linear manifolds, spanned by the eigenvectors associated to a given eigenvalue. So I'm assuming
words like manifolds when they talk about like spaces.
Yeah. So I imagine like eigenmanifold is like actually stretching a space instead of stretching a vector.
Yeah.
Because a vector is like a line, right?
Yeah. But when you have a number of set of vectors, like let's just say you have two vectors.
Now it's a manifold.
Okay. Yeah.
Just more than one vector. Okay. So then, so let me get where was I again? Okay. So in the corresponding eigenmanifolds, the linear manifolds spanned by the eigenvectors associated to a given eigenvalue, also called eigenspaces, play a basic role for the predictive content of the theory. And then he goes on.
Yeah, but I think that's kind of it, right? Like you just kind of setting up what.
Yeah. So it's just showing you the math.
Are, yeah.
And the reason the math is written this way. Like, for instance, they were talking about the Hermitian matrix or the self-adjoint matrix or the self-adjoint state or whatever it was called, B. The reason it needs to be this way is because with these particular matrices, when you take that conjugate transpose, which is just a special mathematical operation, you actually get back real values. So these matrices, these B matrices or these B states can be imaginary states. Of course, we don't know what the hell that means in real life, so you have to find a way to make those into real values. And it just so happens that we have mathematical tools to do that. If you multiply I by itself, so I squared, you get back -1. So the mathematical operation of taking the conjugate of a imaginary, let's say imaginary state, will give you back a real number. So some -1 will pop out somewhere.
Yeah.
And yeah, that's just what it is. It's like you're using kind of math trickery to see if you can fit it onto the real life picture.
Yeah.
And that's what they came up with.
Yeah, by the way, like this all sprung up because they were trying to describe experimental energies that they were getting, and they were like, what the heck is going on? And like, I mean, this stuff wasn't figured out for like at least 20 years. They did not have a good formalism.
Yeah.
You know, but ultimately, I think after Dirac and Heisenberg and everybody came up with like a good picture of, or a good theory, I guess, of quantum mechanics, you were able to come up with the fact that a measurement always causes the system to jump in an eigenstate of the observed quantity. And like it says here, it says, correspondingly, the state vector of the apparatus jumps into the manifold or space or subspace associated to the recorded outcome. So like that just means that like you make a measurement on a system because the type of measurement that you made will put you in certain energy ranges and certain subspaces of that sort of the outcome of the measurement. Damn, that's like super
that was hard.
That's super convoluted.
I lost you a little bit.
Too much jargon, but like
this is really when you get to like quantum stuff, the jargon gets really
math.
heavy.
Yeah, because that's why you need math of like all this other stuff.
Speaking is kind of like, I'm convinced speaking about quantum is kind of just a futile effort. I mean, for maybe for the podcast listeners who really enjoy this stuff to like kind of, especially if you know the math, this is actually probably a little bit easier to
if you know about quantum mechanics, like it's easy to have a fruitful conversation about it.
I just wish there was an easy way to convey it to the general public, but the only way you can do it really is with math like this. And then you have to know like
basic definitions and like there's a number of definitions and operations that you have to be comfortable with.
There's probably a way to simplify it down. I think we could do it.
I thought about the analogy of a card game, like
I read that before.
There's some probability-ish kind of stuff, and that's kind of the issue with quantum mechanics. Like at least that's what they highlight in this. For those of you that will be looking at this document, they say like, how could you, if something is deterministic, how can it be probabilistic? Like, you know what I mean?
Yeah, they
like
were saying,
right?
Yeah,
like,
because quantum is basically a probabilistic system, right?
Yeah.
But then somehow at higher orders of magnitude of, let's say, a collection of particles, like if you have an Avogadro's number of particles, now all of a sudden your system is completely deterministic.
Yeah. Where's the transition, right?
Right.
Yeah.
And even time independent solutions of quantum mechanic systems, aren't they?
Aren't they what?
I was going to say, aren't they deterministic? But they're only deterministic once they collapse the state.
But quantum mechanics in general, I would say it's deterministic, but this is why the language is kind of shitty, I would say. But it's probabilistically deterministic. Like there's only a certain
but is all probability probabilistically deterministic? I think it might be.
What do you mean?
Maybe that's a stupid way to even categorize it, because maybe all probability is probabilistically deterministic in a sense that once you've gotten the probability, then you know what's gonna
you're saying
evolve.
In the classical mechanics we have less things of making it probabilistic. Like in the macro scale we have things like things are in a definitive state.
Well, things are deterministic in classical systems, right? Because we literally can get into.
But I can think about it like a phase thing. Like I attach a phase, and I'm just like, this thing is not going to phase out of existence. It's got to set the probability of it disappearing is zero, essentially.
What do you mean, though?
Like you have a zero probability right now of disappearing from this table, from this chair.
Effectively zero.
Effectively
not zero. Effectively zero.
Effectively zero. Yeah.
Okay.
But is that what you're saying? You're like everything carries a probability?
No, I wasn't saying that. I was saying that that I was wondering if all probabilities might be deterministic at some level or all systems. I don't really know if that's even true. I'm really not even thinking at all about that.
Shoot some darts out here.
Okay, so let's think of some probabilistic systems. So I guess rolling a die.
Yes.
Once you understand...
But quantum mechanics is not like an even
No, I
die.
guess it's not.
It's not
It's
an even
not.
die system either. It's like
Right.
you have weighted probabilities of certain better outcomes depending on...
Right, so I guess quantum is kind of unique because once you've gotten that state collapse, now you know where it's going to go.
Well, you have a certain range of possible values that you know you're going to take on, or you know your system can take, but they're all weighted differently, right?
Yeah.
It depends on the type of measurement.
But I mean, I'm saying like once you've collapsed a particle,
you put it in an eigenstate of that.
you can
of your
determine
measurement.
where it's moving though.
Yeah.
If you collapsed it and you keep it collapsed.
Exactly. Yeah.
Now it's deterministic. Now it's in the classical regime.
Yeah.
So I guess quantum is a probabilistic system.
Yes.
Because only when you collapse it, you bring it into classical land. Right.
Yeah.
So yeah, quantum's
But that's
not
why physicists have a
probabilistically
pro- but that's
deterministic.
why-
It's just probabilistic.
But that's why physicists have a problem with it,
Why?
because you go from probability land to
Determinism.
determinism.
Yeah, it really. I don't know how it makes sense. But then again, I'm like many things in life at the higher levels don't make any sense.
Let me defend my terminology here. I think what I mean by probabilistically deterministic, I mean that when you make a measurement, let's say you're trying to measure the momentum of a particle in a box or something, you will have a certain range of eigenenergies and eigenstates that are possible given the momentum. The energy, you're not going to have an infinite range, you know what I mean?
But that still doesn't imply determinism because anything like a six-sided die is probabilistic. Would you agree?
Yeah, but it's
only got six numbers.
But you only have six possibilities.
Yeah, but it's still probabilistic.
But it's not an infinite number.
Yeah, but infinity does not imply that it's deterministic somehow. Determinism simply means that you can predict all of the results after you have the initial state.
I mean, it's better to say that it is. Okay, my thing is maybe the language. Like, I'm just saying.
Yeah, I think your definition is off.
I'm just saying that like
probability means.
Sure, but I'm saying that I can tell you something about the system that you're only going to have six outcomes rather than an infinite number.
Sure, but that's not
determinism.
Part of the definition of determinism, right?
Okay.
It doesn't have anything to do with the finiteness of the set that you're working with, the set of values. Let's say. It doesn't matter if it's infinite or finite.
Okay.
And neither does probability. Probability just says that there is a, what would you say? There is a weighted outcome between a set of at least two or more possible outcomes.
That's fair.
So that's the only distinction between the two. So probability, I would say quantum is a probabilistic system. Classical mechanics is a deterministic system.
Okay.
Yeah.
Fair enough.
Yeah.
And I was going to say something else, but I wanted to get to another point in this article here. Had to be okay. So we'll go to the birth of collapse series. No, you wanted to go to this other topic, right? The third. What did you say?
I don't know.
We could definitely talk about this. This is a whole ass subject, like of just.
Yeah, it is.
There's so rich. There's so much richness to this.
I wish I would have read the
because it's leading edge.
Like,
oh, you will, Terence. You will. The status of collapse models in recent positions. So they talk about the macro problem, right? The macro objectification problem has been at the center and the most challenging debate originated by the quantum view of natural processes or whatever. And all that means is that like the transition, how you as a macro object interact with a microstate, basically quantum system.
Right.
There's a coupling of energies. Like in quantum mechanics, we isolate we try to isolate the system energetically so we can describe it using a Hamiltonian of like the kinetic energy of the particle.
Right.
We make it as ideal as possible, right?
Yeah, so we don't have to describe all of the interactions that are around it, right?
Yeah.
Because, for example, the thing that some of you may not know in quantum mechanics is like, you've probably heard that a particle is described by a wave function, right? Mm-hmm. So a wave function basically just quantifies where it can be anywhere in space. Mm-hmm. Sorry. So if you have a particle in a box, then the wave function is quantified by the length of the box. It can exist outside of the box sometimes, but it's got a value related to the size of the box. Mm-hmm. Now, something that's not obvious, the non-obvious part is if you have two particles in a box, let's say, both of them are interacting now. So they both have some kind of coupling effect where now they're described...
And selection rules, right? Like if they're like both electrons or something, they now have allowed like configurations, right?
Yeah. So now they have this property where they're governed by a single wave function still. Mm-hmm. So it's not two independent wave functions. Now it's a cumulative wave function between the two. They have some kind of interaction now.
Yeah.
So this is the interesting thing here is just like we're pretty good at understanding like how multiple particles can form their wave function when we understand it with a small enough amount of particles, let's say. But we don't know what an Avogadro's number of particles
like macro state
look like
interacting. Well, like you get a nasty wave function. I'll say that.
Yeah.
But like you do.
But I'm pretty sure we don't know how to write that down.
Computationally.
Yeah. Yeah, it's an untenable amount of particles to where we could not write down what the wave function of an Avogadro's number of electrons would be.
A pain in the ass.
Yeah, it would literally take you like to the end of the universe probably in time.
I'm sure there are techniques, but like I mean, I think von Neumann showed that, and I think you took a professor that actually showed that you get statistical mechanics from quantum mechanics.
Yeah, but that's not using computational methods. That's using analytical methods, right?
Right. But you make certain assumptions, I guess, right? That lead you to...
Yeah, you don't have to do any counting. You just say, I'm going to take the sum of all n particles or something.
Yeah. No, because von Neumann, I think, showed in one of his books, if I remember correctly, that you have like because he tried to tackle this problem of like how the macro state interacts with the quantum system. Mm-hmm. And he imagined like, well, if you have an SEM probe almost, right?
Yeah.
The SEM probe has like whatever atomic elements that are, at the tip of the SEM probe.
Right.
So it's like you have a certain number of atoms, and they're going to have their own potential, and they're going to interact with the Hamiltonian of your system, and how does that interaction affect the wave function and stuff like that.
Right.
And yeah, it's just it's a very, you can go see this in von Neumann's book. It came out in 1926. But
cool.
It's funny that quantum mechanics has not changed very much in 100 years.
And it shouldn't, right? That's when you know the physics is good.
I guess it shouldn't, but it's still like...
We hope it doesn't change too much.
I mean, we're at a crossroads, but this is why you see stuff like this where a lot of physicists are like, we're at a standstill. We need to find something's going on. We haven't made many advances in 100 years.
Right.
There's something we need to find.
If you had to guess, where would you think that quantum understanding would give us the most bang for our buck?
I think so.
Okay.
Metaphysically understanding it, physically understanding it,
yeah. Well, I don't want to say metaphysically because it's still physics, right?
Well, it's still physics, but you're looking at the bigger picture in a sense. Right?
Yeah.
That's what I mean by metaphysics.
Actually understanding it.
Yeah. Like as opposed to looking at the math and calculating and we know how it works, obviously.
Yeah.
Because we do it, but
and it's very.
But why?
Predictive.
But why does it work?
Right. That's the key. That's where
and that's
Sean
really
Carroll
all of
and guys
physics
like that.
is like supposed to be like.
Yeah.
At the end of the day, I think it's like why, answering the question why.
Yeah. That's kind of the whole point, right?
Yeah, true.
But I guess how is useful too, because I mean that yields a lot of stuff if you know how to do it.
But it's always how and why, not why and how.
Not always.
You ever think about that?
Not always. Deep one.
It's always how is the quantum system doing instead of why. No one ever asks. But yeah, so man, wow.
What's our time, by the way?
There's a lot more to discuss, and we're almost at 50 minutes. Let me just, I want to hit this article. I want to hit you with this article, Terrence.
What you got? Another quantum collapse one?
No. This is for the listeners too.
Okay.
This should be a fun one. Scientific American just had an article that came out in, I guess earlier this year. World's first living machine created using frog cells and artificial intelligence. Did you hear about this?
Living machine. No.
Scientists used computer algorithms to develop a programmable organism made of frog DNA. This is in Scientific American.
And what is the DNA, like logic gates or something?
Well, so they just say they take frog cells from embryos and grow them into new organisms that were basically created by certain AI algorithms. And you get basically the first living machine, quote unquote. So the original stem cells came from frogs, the African clawed frog, Xenopus laevis. These so-called xenobots is what they're calling them. Are you ready for the xenobot revolution?
The buzzy, just sensational stuff, man. It's just so annoying. Why is everybody gonna make everything so sensational?
Come on, man. You're not ready for the xenobots, man? The xenobot takeover?
We got xenomorphs and shit here now.
I'm gonna love the xenobot TV show on Saturday mornings or whatever they have now, I guess. They don't resemble any known amphibians, however. The tiny blobs measure only 1 millimeter wide and are made of living tissue that biologists assembled into bodies designed by computer models. These mobile organisms can move independently and collectively, can self-heal wounds, and survive for weeks at a time, and could potentially be used to transport medicines inside a patient's body.
Wow.
They're neither traditional robot nor known species of animal. Joshua Bongard, a computer scientist and robotics expert at the University of Vermont, said, it's a new class of organism, a living programmable organism, I guess. Algorithms shaped the evolution of xenobots. They grew from skin and heart stem cells into tissue clumps of several hundred cells and moved impulses generated by heart muscle tissue. And there's no external control from a remote control or some kind of electrical impulse or anything. It's completely autonomous.
And it wants to survive and everything?
Apparently. I don't know. It's imbued with this organism, this AI, algorithm, how to grow.
Wait, so how is the AI embedded into it? I don't understand.
Apparently it's like a they're analogizing it, saying it's like a wind-up toy. It's like, maybe they'll go into the AI part
here. So it goes and goes until it runs out of juice or whatever.
Biologists fed a computer constraints for the autonomous xenobots, such as the maximum muscle power of their tissues and how they might move through a watery environment. Then the algorithm produced generations of the tiny organisms. The best performing bots would reproduce inside the algorithm under the guidance of the AI algorithm or whatever.
Okay.
And just as evolution works in the natural world, the less successful forms are deleted by the computer program or are destroyed. Eventually, it gave designs that were transferable to real cells, and that was a breakthrough. And so, the study authors then brought these designs to life, piecing stem cells together to form self-powered 3D shapes designed by the evolution algorithm. Skin cells held the xenobots together and the beating of heart tissue and propelled the bots through water and petri dish for days and even weeks without needing additional nutrients. And they were able to repair significant damage. So what do you think, Terrence? Are you ready for the xenobot future? Would you take a shot of xenobots?
I would if it could give me some some superhuman healing or something. I'd be down for that.
Xenobot.
They're probably not. I would imagine they wouldn't be too invasive. I would hope.
What, the xenobots?
Yeah, I would hope. But then maybe it's the CIA's injecting me with trackers and
But what if xenobots? Would you take xenobots or nanoparticles for drug delivery? Because at least
probably xenobots, because at least they're organic material, right?
And they'd be cute, right? Imagine if they grow big and you have a xenobot as a pet
inside of me. I don't know if I want that.
No. I'm saying around the house, you have it in a petri dish. And
I see.
You know what I mean? You have a xenobot farm.
I'm imagining that little thing from Stranger Things too. The little
blobby thing.
Yeah.
Yeah. That's literally what they said. It's like an amorphous blob, and it just moves around doing things. Yeah.
Interesting.
Yeah.
I really would like to know more about it because I'm like a little bit confused in how it actually like.
What are your questions? I'm a xenobot expert.
I just want to know how it like. How does it eat and like how does it get energy to move?
How does it get energy to move? What do you mean? It's
like how does it survive? Like how does
I think they give it nutrients.
But it was saying that it was autonomous and it was able to get its own nutrients, right?
Yeah, because petri dishes are like they have like nutrients in them, but they
but how does it get them? I wonder. Does it like actually do like?
I think it does its own process of like eating and stuff.
I want to know what that is though, because we know like
it's a biological thing, bro. They just fucking do it.
Well, we know how normal cells do it, right? They like extend,
yes,
and then they let in some protein or something.
Yeah, but
or
they
some
said
ATP or something like that.
Yeah, they said they constructed a what is it called? A stem cell like or skin. They give it a layer of skin of an epidermis. So the epidermis I think would allow certain
things to pass through and out.
Yeah.
Okay.
Like if it had like it would be a self-regulated. I guess that's what they mean. It's like self-regulating and autonomous. Like maybe the stem cells have memory of how to let certain nutrients in. Maybe I don't know. What do you? Is that? That's my take.
It's all speculation.
It's all speculation.
Yeah, we got some. I got some questions I gotta ask.
Let's get a xenobot expert on the show.
Yeah, we need one. Maybe we can.
University of Vermont. It's University of Vermont, man.
Well, that sounds definitely attainable.
They're just grad students. We could talk to grad students. Just be like,
no offense to University of Vermont.
I'm just saying university students are more attainable.
Yeah.
Like you can talk about your research, right? And they'll be like, yeah.
You mean the xenobots?
Yeah.
Say no more.
We want to know about the xenobots that you have in your lab.
Who are you working for?
Yeah. I love the marketing strategy for this though.
Well, it's
the word xenobot is just amazing.
That's what I'm saying. I'm always astounded by the number of sensational shit people come up with. The media was loving that name.
Mm-hmm. So yeah, the AI basically it emulates natural selection, and it says here that the AI determines the tissue configurations for the xenobot to perform a specified task, such as moving through fluids or carrying a payload. And then the most promising designs are sculpted with forceps and cauterizing irons. Wow. Then set free in petri dishes where the specks of amphibian flesh live for about a week before decomposing.
Oh, damn. It sounds like they kind of make those xenobots themselves by hand. Damn. So some poor graduate student spending his whole weekend making xenobots with a fucking soldering iron and forceps. That sucks,
yeah,
man.
Dude, I know. They're programmed can you imagine, like, it's a millimeter in size.
Yeah, it's probably so hard to do, I'd imagine.
I know, they have like a little microscope.
Yeah, he's probably looking in the microscope just all day. Fucking up xenobots.
Stitching the xenobot up. Just being like, fuck. Behaviors are programmed entirely through the structural arrangement of the pulsating heartbeat cells held in the matrix of rigid skin cells. So I imagine they have like a matrix, like cut up skin grafts. I imagine they have a skin graft thing, and then they put the stem cells or something, and then the stem cells have programmed, I imagine, DNA or something.
Yeah.
And then
that responds in some specific way.
Yeah, to stimuli or something.
Yeah. Sounds clever for sure.
Uh-huh.
Sounds clever for sure.
Yeah. But that's xenobots, bro. You ready for the xenobot future?
Hell yeah. Give me them xenobots with some COVID and vaccine in them.
Yeah. I'm ready for it. I'm ready for it.
You ready for it too?
I'm ready for it. Better
Are you
than
gonna
nanoparticles.
take the COVID vaccine, by the way?
Yeah, I am.
Like immediately?
Well, no,
you're going to go first wave?
We're not on the list.
Oh,
you might be on the list.
I thought it said 30 and up or something.
Oh, really?
I don't know. I might be making that up. I just saw memes of people saying, 30-year-olds are going to get first or something.
No. I think I remember hearing the official list being that apparently you have to keep the vaccines at negative 90 degrees Celsius.
Oof.
To be transported.
Oh, damn.
Yeah. So,
but they got the means to do that.
And it only lasts a couple of days, according to, like, you need to really, it needs to have stringent storage specifications.
Oh, wow.
Otherwise, the vaccine loses efficacy, and then you're just,
It's useless.
Yeah. So, and the thing is, right now, the trial the trial standard is 3 follow-up shots. So you have to take the first one.
Damn.
Yeah, you have to take the first one and then follow up a couple, maybe weeks or months, or a month or so.
And that's when you'll be immune.
And yeah, so you get full immunity because you get like booster shots and stuff. So like, yeah, it'll take up to I don't know how long, but
So we got a road ahead of us still.
yeah, we do.
Damn it.
The general population, according to the timeline right now, is that by May, most civilians will.
Oh, you think
get
May?
it. Yeah.
Okay.
By May.
May's pretty good timeline.
That's what I figured. I was
Yeah.
like, I don't see us getting a vaccine until like next summer.
Yeah.
So
May would be very good.
yeah.
May would be very
Plus,
good.
this is huge, man. Like this is.
Yeah.
I don't think the world has ever come together. This is like the world war. This is like a world war.
Yeah.
Against, right.
Right. And
This is going to go in the history books.
Yeah.
Yeah.
Could you imagine if we like just focused all our energies on like single
Things like
vaccines
this.
like this all
Yeah.
the time in science, or like we just want to crack fusion and we just spent all our shit just
A whole
going
year.
for fusion, and then we just
Yeah.
it's like, man, people don't realize the power of science if it actually had money
Yeah. Or
and
like yeah.
good like attention given to it, like good resources allocated to it.
Do you think climate science? You think you do that with climate
Anything.
climate change?
Anything.
If the whole world just for a
Yeah.
whole year was like, we're going to change everything to renewable energy.
Probably that's probably what it's going to come down to too, because we can't ever like act in time, so it's probably going to come
It's
down
always
to us
waiting till
like,
the last
okay,
minute.
we're about to die in like
Yeah.
in like the next couple of years.
Yeah.
We need to crack down.
No, it took the threat of a virus that will wipe out 1% of the world population
Yeah.
for us to like. I mean, because you see the financial impact, right? Like,
Yeah.
you see how much. Yeah, 1% of the population of 7 billion
Yeah.
is huge.
Yeah.
Yeah,
And I hope people
economically.
just understand like this. I hope this gives people an understanding of where the line of like how much we have shit taken care of.
Yeah.
Like you should really understand that the level of shit that we have taken care of is not that much.
Right. Yeah.
Like people are not thinking about like existential level threats that often.
yeah.
Like you may feel comfortable in this daily life that we
Yeah.
have, because a lot of the stuff, close to us is taken care of, and government's on their shit
yeah.
in some level. But just remember, at the end of the day, like these existential level threats, we are always susceptible.
Yeah. Because the virus was an existential threat until.
Yeah.
Yeah.
Now we finally are
Yeah.
getting the means to understand how to deal with a pandemic.
Yeah.
But sometimes you may not have the luxury to deal with an existential threat level virus
Yeah.
once and then learn from that and come back a second time.
Yeah.
Sometimes that once is it.
Yeah. Exactly.
So you really,
All it takes is really one catastrophic event to
Yeah.
wipe out all.
if this pandemic was the right kind of deadly, like
yeah.
for like imagine if it killed like
5%,
everyone.
5 or 10%, like the 10% was the Spanish flu, right?
Well, just imagine if it didn't really kill just elderly. Let's imagine it killed
every age group.
every age group with the same amount of percentage
Yeah.
as the elderly. Then you would really understand, like,
Yeah, huge.
Yeah, that would be really bad.
I was telling Juan this one time. I think this was the perfect pandemic virus for us to get
Yeah.
because it only affected old people
Mhm.
who they're kind of sickly anyway, or in a very adverse way. I'm saying,
Mhm.
and then the effects of it aren't really that bad.
Yeah.
Like it's like a flu-like effect.
Mhm.
And then the transitions rate is really high, so it gives us an understanding of how
Yeah.
a good spreading virus
Yeah.
can propagate.
Mhm.
So we really got lucky with this one in terms of
Yeah.
understanding how a pandemic virus can go, because it's kind of a benign one for what it
Yeah.
could have been.
Yeah, I'm just ready for the xenobots to come and save us from the next virus. I'm ready for us to
You
unleash
think the xenobots are gonna step in, huh?
unleash the xenobots. That's like the next president in 2024. President Kamala Harris, unleash. Yeah, ma'am, we have President Harris. We have a new COVID-24 at our doorstep. What do we do? And she's like, I have to make a call. Because Kamala Harris is a secret listener to the show.
Yeah.
And then she's like, then she calls up the University of Vermont. Hello?
Uh-huh.
Unleash the xenobots.
Just like a swarm.
yeah.
Swarm.
No,
of
they literally
blobs.
use like airplanes and just drop them on everybody, and you just
That'd be
inhale
cool.
them. You just
Yeah.
inhale them, you know, and then that's it.
I was imagining more like a scene from that movie. What is it? The Day After Tomorrow with Keanu Reeves. Is that what the one it is?
Day after tomorrow.
Yeah, he's like an alien in the movie, and there's like a bunch of nanobots get unleashed.
The hell?
You never saw that one?
I've never
it's
seen
really
it.
goofy.
Day after tomorrow. Oh yeah,
Yeah.
where it's like repeat. He's like a Groundhog Day scenario.
No, that's Edge of Tomorrow
Oh,
with Tom Cruise. Yeah. This one's Keanu.
Yeah.
If you didn't see that one, it's kind of it's a fun watch, I guess.
Okay.
It's a forgettable movie though. I don't remember any
What
of the
about
plot
it?
really. But they have like this wave of nanobots that just overtake. It's more of like killing society.
I see.
But it's just like a giant wave of just these
Yeah.
nanobots.
See, I'm more welcoming of like the idea of cute little organisms named xenobots than I am of nanoparticle or nanomachines.
Yeah.
Like-
Things that are organic are more trustworthy. For some reason.
I have cute little xenobots fighting in my body. They're trying to help me survive.
You imagine them almost with like little
Googly eyes.
Yeah, googly eyes and smiley faces. There's something about organic things that make you just feel safer for some reason.
Damn, Terrence, I need to put you on the marketing team, dude. Yeah. We have
Xenobot.
to. You as a guy in the suit, just coming into the meetings, a bunch of scientists, just be like, we have to give them. The public wants googly eyes on their xenobots. This is how we make them palatable.
Or
to
cute
the public.
anime eyes.
Or cute anime eyes. Just figure it out. Figure it out. You know what I mean? And then you go and tell the stakeholders, that, you're solving the issue of the public falling in love with xenobots. So you market them as like plushy toys.
Yeah, exactly. Selling Beanie Baby Xenobots. There's a throwback if anybody remembers Beanie Babies.
Yeah, Beanie Babies.
Leave it in the comments.
You start a show. You start a Netflix show with xenobots and then different kinds. I could already see it.
There you go, like a little cute like cartoon.
Yeah, exactly. All in the name of propaganda.
Yeah.
When we're gonna need them. Anyway, this is the whole thing. Anyway, folks. I hope you enjoyed the show.
Yeah.
Please like, comment, subscribe, share. And follow us on our socials, right?
Yes, Eigenbros.com, Eigenbros on Instagram, Eigenbros on Twitter, Eigenbros2 on TikTok.
Yeah.
Thank you once again to the Patreon people. Guys, if you like our stuff, make sure to check out that Patreon. It's Eigenbros on Patreon as well. And I think that's it.
Yeah. See you later.
See you guys.
Bye.